This video is going to be about free fall. More can be found about free fall in the links to some other websites I like in the description of this video, as well as our OpenStax book pages 67 to 75. OpenStax can be found online and also in the About section of our Google Classroom page. Free fall is an idealized motion in which air resistance is neglected and acceleration is nearly constant. So some bullet points on what that means. The only force acting on the object is gravity. There's no air resistance or any other force. The fall distance needs to be relatively small compared to the radius of the Earth, so that usually just means we're dropping stuff close to the surface of the Earth or for short distances. In free fall, all objects, regardless of mass, fall with a constant acceleration or at a constant rate, which is g. That means how quickly they speed up is the same, regardless of their mass, and little g is equal to 9.80 meters per second squared. On the AP exam, you can just estimate this at 10 meters per second squared, which is convenient for quick calculation and also canceling out with pi squared. In the lab, we will use 9.80 though. Because acceleration is constant, free fall is a type of uniformly accelerated motion, and we can use the kinematic equations that we've already derived. First, we'll start with just a simple diagram and a simple explanation, or example rather, and then see if we can come up with some graphical representations of what free fall would look like. So here I have a situation in which I have a red ball that I'm going to throw up. It's going to leave my hand with the velocity upward at time t0. It's going to reach its highest point at time t1, and it's going to return to my hand at time t2. Even though I can't draw these perfectly straight in line because all my letters would be right on top of each other, I would like for you to imagine that this ball is traveling perfectly straight upward and perfectly straight back downward, and there's actually no change in position in the horizontal direction. Because there is just a change in direction in the vertical position, or change in position in the vertical direction, rather, I'm going to use y's to indicate positions. So y0 indicates its initial position, y1 position at its highest height, and y2 when it comes back to its original position in my hand. So remember that this would mean that the total displacement is 0. It returns to my hand, but it does have a net distance, or positive distance it travels, the sum of its distance upwards and downwards added together. I've indicated that the upward direction is going to be positive and the downward direction negative over there, and I've drawn in my corresponding velocities and positions with the same subscripts to keep track of stuff. So in this example, just to be clear, I do mean that initially the ball is traveling with some positive velocity upward, because I said up is positive, and it comes back down in the final position at y2. It has some final velocity downward. Now, of my three graphs, this time I'm using y versus t to indicate my position versus time graph, because I have just change in position in the y direction. And I also have my velocity time and acceleration time just as before. I need to set my 0 line. I'm going to choose that at a convenient place, which is going to be just where the ball leaves my hand with its initial upward velocity and where it returns with its final downward velocity. That's the 0 line in dotted blue. Some things I also know that are going to be helpful for when I start this graphing. I know that when the ball reaches its highest point, just for a moment, an instant in time, it has a velocity of 0. So once it reaches that highest point, it has a 0 meters per second velocity, and then it starts to return to my hand, and that's when its direction of its velocity has changed, and it's flipped from positive to negative. I also know that initially when I threw it upward, because I called it positive, it has an initial velocity v0 that is upwards or positive, and a final velocity v2 which is downwards or negative. This helps me to plot my graphs because I know right in the middle at t1, or halfway through my position time graph, I should have a flat 0 slope to indicate velocity is 0. I also know that I should have an upward positive slope for the first half of my graph because it's traveling upwards in the positive direction. And I also know I should have a negative slope in the second half of my position time graph because the slope is negative, indicating a negative or downward velocity. I can then interpret what my velocity, or produce my velocity time graph from my position time graph, knowing that the VT graph is just going to be a plot of the slope as it changes on the position time graph. So the first half I have a changing velocity that is changing towards the negative. It's slowing down, but the whole time in the first half of the graph it is a positive velocity. The object is a velocity that is upward. It is still traveling upward. Then halfway through it has at time t1 a velocity of 0, which is halfway through my VT graph, and the second half it has a velocity that is increasing in the negative direction. It's speeding up on its way back down to my hand, and you can see that on my graph. You can see also that the slope of my velocity time graph is just some constant value, and it's a negative slope, and that's consistent with my negative downward direction I defined in my picture. This also means that my acceleration time graph should indicate that my acceleration is a constant value. They're placed on a constant number on the y-axis, and that value should be minus 9.80 meters per second squared. Here are some indications on the graph that I've drawn that help me identify that I've drawn them properly and that they correspond to the physical scenario I described. Notice that this value for A over there should be minus 9.80 meters per second squared because I defined down as negative. I've also drawn in some blue slopes on my position time graph to help me indicate that I've drawn it correctly. And also an important note on my velocity time graph that the initial velocity, the positive velocity upward when it leaves my hand, should be equal in magnitude to the final velocity downward when it returns to my hand. We can show this mathematically and also try to measure it in the lab, but this is just a case of free fall when we have no air resistance, that the velocity is going to be exactly the same as it leaves my hand when it returns to my hand. That's why it's very important. When you shoot something upward and it comes back down to hit you, it's going to hit you with the same speed with which you shot it upward. Now I want you to imagine that we flipped the directions now and I called up negative and down positive. If I do that, the graphs that I should produce would be the ones that are in green. You can see all the way on the acceleration time graph, the acceleration has become a positive 9.80 meters per second squared. This would make my velocity changing from an initial minus velocity or negative velocity, cutting through the zero line again at halfway through the object's flight, and then ending with a positive velocity at the end. All the while it has a positive slope which corresponds to my positive acceleration. You can also see on that position time graph, if I go back just to that slide real quick, hold on. My position time graph has just been inverted as well, reflected over the x-axis, and this is also consistent with changing my directions. Realize that the physical scenario is going to be completely the same, but just changing my conventions, flipping the directions that I want to call positive or negative, doesn't change the actual physical situation, it just changes how we represent it mathematically, which includes our graphs. But still, we interpret the graphs the same way and we come up with the same conclusion about the physical situation. Next section we'll look just briefly at our kinematic equations as we saw them before and then how they relate to their use in free fall. It's the exact same equations in free fall except we replace some variables and are just very careful about our sign usage. So those are the original four kinematic equations I derived in a previous video and now I'm going to write them over again except for free fall and I'm assuming up is positive and down is negative. That's very important. In this example, I assume up is positive and down is negative. So notice in the first equation, all that's changed is the minus sign. It goes from a positive a to a minus g because I said down was negative. The acceleration is known to be a certain value called g. That's a physical constant equal to 9.80 meters per second squared. And because it's downward, that has to be a minus sign there. If I call down positive, then that equation would change to v equals v naught plus gt. The second equation shows delta y instead of delta x because I've decided that my vertical change in position should be indicated by y values that are changing. This is very helpful so that we can use x values for horizontal motion and y values for vertical motion when we break projectile and other two-dimensional motions into their x and y components. So for free fall, since that's a vertical motion, I'm going to use delta y instead of delta x to indicate a change in position or a vertical displacement. That's equal again to a v naught t minus, because it's down is negative, 1/2 g because it's a known acceleration that's 9.80, and so I have to use my symbol g, times t squared. The third equation again has delta y instead of delta x for the same reason indicated for the equation 2, and then I just have my v naught and v as before with the time t. My final equation at the bottom, the only thing that's changed there again is the minus sign, because the direction downward is negative, and the acceleration is a known value g, which is directed always downward. I also have a delta y there for the same reason. The free fall equations can also be modified slightly if you know that your v naught or initial velocity is 0. That's very convenient and can be very helpful in the AP multiple choice exam parts when you're just trying to do a kind of a quick assessment of something. If the v naught is 0, then that v naught from my center column of equations disappears from the equation. And this may be like if I'm dropping something off the balcony or what have you, and the initial velocity of the object is 0, and I'm going to let it go, and it's going to speed up, and maybe want to find out what its final velocity is when it hits the ground. So those equations on the right-hand column or third column are v equals minus gt, delta y equals minus 1/2 gt squared, delta y equals 1/2 vt, and v squared equals minus 2g delta y. Very helpful just to be able to know what those should look like when v naught equals 0. One other thing to notice, those first two equations there in the third column, the first one shows that the final velocity of the particle once it's dropped is directly proportional to the time. The second equation shows that the height it falls through, or the distance it falls, is directly proportional to the time squared. Those are good relationships to know. Velocity of the falling object is directly related to time, but the height it falls through is not. It's directly related to the time squared. So if I double my time, I actually quadruple the height something falls through. If I double the time, its final velocity is only going to double. Good quantitative reasoning skill that are going to be asked on the AP exam, or questions like that. Final note in red, watch your signs, be careful, and often it's best to draw a quick diagram to keep track of or check yourself in terms of which directions you're using and whether you're applying your graphs and kinematic equations properly to the actual physical scenario. What I'm going to look at real quick here is one particular kinematic equation that you may want to use for your lab on Monday. I'm going to describe kind of what the scenario or setup's going to be. Say we're standing on the balcony up there, and so I got that gray line that represents maybe the handrail, okay? And I have, again, a red ball, and I'm going to drop the ball, and you can see it's going to come down and probably hit the ground there, and at that bottom position, I'm indicating that the ball is still moving, so that final moment in time, T1, is the moment just before the ball hits the ground. I have some other kinematic variables I can list for each position. A, the acceleration, that should be the acceleration due to gravity. V naught, its initial velocity. Y naught, its initial y position. T naught, its initial time. And the corresponding things for the final time, T1, down there at the bottom. I'm going to go ahead and define up as positive and down as negative. It's always important that you define your directions before you get going. In this lab, I'm going to say, okay, I know A is supposed to be equal to little g, which is 9.80 meters per second squared in the downward direction, but I want you to try and figure out if that's true. So we're going to let A be a question mark. We don't quite know what that value should be. Some things we do know, though, the initial velocity should be 0 meters per second if we're just going to let something go, so you can let V naught equal 0, and we know that the height that it falls through is going to be some change in vertical position, which would be y1, its final position, minus y0, and that can be our delta y, or also just the height or fall distance. Just be mindful that that's downward, and therefore going to be a negative value if you call down negative. So the free fall lab that I want you to prepare for Monday is to think about this problem. Determine the acceleration due to gravity g experimentally. We know a should be equal to g. We have some stuff we can drop, and you're probably going to want to find some height you can drop something from. And in terms of designing this, I'd like you to come up with an equation, derive, meaning come up with from basically first principles or your math, your understanding of kinematics and free fall, derive an equation for the acceleration in terms of the kinematic variables. So I have time, I have initial velocity, I have final velocity, I have displacement, and I have acceleration. So I want you to derive an equation for the acceleration in terms of those other variables. Again, I know we can say that g should be 9.80 meters per second squared, but I want to see how close we can get to it, and who knows, maybe g is slightly different here in Baton Rouge. Good experiment should show us what it is, and since we do have an understanding of how we can talk about uncertainty and error, you can say maybe how far off your actual calculated value could be depending on the accuracy of your measurements, or precision rather. Once you derive an equation, you want to make sure you can refine it, determine if you can practically measure the stuff that you are going to use in your equation to find the acceleration. If not, derive a different one and try to find something that you can come into class on Monday and say, okay, this is an approach we should use to try and figure out what the acceleration is when I drop something off the balcony. We know it should be approximately equal to 9.80, but I want you to find out a way that you can try and test that, and we need to know how to do the math, which means moving around the literal equations in order to do that. So one equation that might be very, very, very helpful, I've boxed in orange, which is one of those modified kinematic equations for free fall when V naught equals 0. And that's over on the left. We do have one more problem that we'll come back to, and I'll just introduce it briefly. This is going to be a fun one. It also involves free fall and having an initial velocity of something. This is something else to think about this weekend as well before we get into projectile motion. It's certainly something we're going to need to know, because if we're going to launch projectiles, we need to know how fast we're shooting them. So this is an example of maybe some cannon there done in blue that's shooting an orange ball upward with some velocity that's unknown. I've stated some information there that you can see, including that the highest height that it reaches at T1 is where its velocity V1 should be equal to 0. I've called up positive and down negative, and this will be a case when, after we complete our lab on Monday, we should be pretty confident that the acceleration due to gravity is actually 9.80 meters per second squared. So this problem that you can start to think about as well is to derive an equation for the exit velocity of the cannonball, or the little orange ball, as it leaves the cannon in terms of the kinematic variables that I've listed there, generic V final, V naught, T, delta Y, and any relevant physical constants that may or may not include g.